All right, thank you, Shu Xiang. Can everybody hear me okay?
I can hear you very good.
Okay, so yeah, thank you everybody for coming to this talk. Um, my name is Peter Bradshaw, and this talk is going to be based on a paper that's joint work with Tomasz Masharzik and Ladislav Stacho. And we're all from Simon Fraser University in British Columbia, Canada, for those who are joining from other places. So um, the talk that I'm going to be giving today is about the notion of list colorings. Oh, there we go. About the notion of list colorings, which most of you are probably familiar with, but for those who aren't, I'll give a definition of what a list coloring is. So in the list coloring problem, what we have is we have a graph like the one shown here, and each vertex of the graph has a corresponding list of colors. And the goal is to give every vertex in the graph a color from its list in such a way that no two adjacent vertices receive the same color. And the list coloring problem can be a theoretical model for real life scheduling problems. So for example, if we have events that we wish to schedule at certain times, then we can represent each event with a vertex, and we can represent possible times to schedule the events with colors. And then if two events can't be scheduled at the same time, then we can add an edge between the corresponding vertices so that those vertices cannot be colored with the same color. All right, so keeping in mind that list coloring can be a theoretical model for scheduling, we can think, is it possible for list coloring um, to model other aspects of scheduling problems? And in particular, when we schedule things in real life, when we schedule events, it often happens that we have preferences for the way that things might be scheduled. So for example, if I have 4 events represented by the vertices here, maybe I prefer the event corresponding to this vertex here to be scheduled at 8 a.m. Maybe I also prefer the event corresponding to this vertex here also to be scheduled at 8 a.m. So in the list coloring model, I can model my scheduling preferences by saying that I would prefer for this vertex here to be colored red, and I would also prefer for this vertex here to be colored red. And then in the flexible list coloring problem, what we do is we consider graphs like this one with color lists like the ones shown here, and also with coloring preferences like the preferences shown here. And what we try to do is we try to find a proper list coloring on the graph that satisfies a positive fraction of all of the coloring preferences. So I purposely chose an example of a set of preferences that cannot all be satisfied at the same time. So here I have a proper list coloring that satisfies half of my preferences. I have 2 coloring preferences and I satisfy one of them. And since half is a positive fraction, and since the goal of the flexible list coloring problem is to satisfy a positive fraction of your coloring preferences, um, I'm happy with this list coloring on this graph because it satisfies half of my preferences. Okay, so now that we've seen this example, we can move to a formal definition of the list coloring problem, the flexible list coloring problem. So first, let's remember that we say that a graph is k-choosable if whenever each vertex in the graph receives a list of k colors, then those lists admit a proper list coloring on the graph. So k-choosable just means list colorable with lists of size k. Then recently in the paper that introduced this notion of flexible list coloring, these authors, Dvorak, Norin, and Postel, defined a graph. They said that a graph is epsilon flexibly k-choosable if for all assignments of color lists of size k, and also for any set of coloring preferences on a subset of vertices of the graph. We say that the graph is epsilon flexibly k-choosable if you can always find a list coloring that satisfies at least a fraction of epsilon, at least a proportion of epsilon of the coloring preferences. So to make it more clear what I mean by that, in this example that I have from the last slide, I showed an example of this graph, which has color lists of size 3 at every vertex, and I have a set of 2 preferences on a subset of vertices in the graph. and I was able to find a list coloring that satisfies half of my preferences. So if it were the case that for all assignments of lists of size 3 and for all possible coloring preferences, if I were always able to satisfy half of the coloring preferences with some proper list coloring, then I would say that this graph is 1/2 flexibly 3 choosable, and the 1/2 would correspond to the proportion of coloring preferences satisfied, and then the 3 would correspond to the sizes of the lists. And I should point out the coloring preferences can be on any subset of vertices. They can be on one vertex, they can be on all the vertices. They can be on 0 vertices, but then it's trivial, so we don't consider that case. But it can be any vertex subset that has coloring preferences. Okay, so with this definition in place, I can start to introduce how we considered this definition in our paper. So we considered the problem of flexible list coloring on infinite graph families because it's a more interesting problem in this setting. Also, I should mention, some of you may be wondering why we use list colorings instead of just normal graph colorings. The reason is because if the goal is to satisfy a positive fraction of your coloring preferences, then if you have k colors in a graph, it's always satisfied to satisfy 1/k of all of your coloring preferences just by permuting the colors. So essentially, if you just use normal graph colorings, then the problem is kind of trivial and it's not very interesting. So it's much more interesting when you use list coloring. Anyway, though, if we have an infinite graph family, we say that the whole graph family is epsilon flexibly k choosable if there exists some value epsilon greater than 0 such that each member, I'm sorry, I messed up the definition. Basically, if you have a graph family G that's infinite and every member of the graph family is epsilon flexibly k choosable, then we say that the whole graph family is just flexibly k choosable. So if every member is epsilon flexibly k choosable for some universal epsilon, then we say that the whole family is flexibly k choosable. I'll give an example, which is the family of trees. It's not too hard to show that if you take any tree, no matter how big or small, and then you give each vertex in the tree a list of 2 colors, and then you choose some set of coloring preferences on a vertex subset of the tree, then you can always find a proper list coloring that satisfies at least half of your preferences. So that means every tree is 1/2 flexibly 2 choosable, and that implies that the family of trees is just flexibly 2 choosable. And this definition kind of implies that often we don't care precisely what this value of epsilon is. All that we care about is that there exists some value epsilon that's greater than 0 and that's universal. That is, it doesn't depend on the size of any particular member of the graph family. And we're more interested in showing that a graph family is flexibly k choosable for some small value of k. So we're more interested in optimizing k than optimizing epsilon. Okay, so with that definition in place, now I can introduce what we call the meta question of flexibility, which asks, if G is a graph class that is known to be k choosable, is that graph class also flexibly k choosable? And this question is interesting because sometimes the answer is yes, and sometimes it's no. So that means it's worth considering on individual classes of graphs because you can't be sure what the answer will be. An example of when the answer is yes to this meta question is triangle-free planar graphs. So it's not too hard to show that triangle-free planar graphs are 3 degenerate, and therefore they are 4 choosable. But it was shown recently that triangle-free planar graphs are also flexibly 4 choosable. So there exists some universal constant epsilon, such that for any triangle-free planar graph and any set of coloring preferences, you can always find a list coloring with lists of size 4 that satisfy a proportion of epsilon of your coloring preferences. An example of when the answer is no, however, would be the class of even cycles. So even cycles can be shown to be 2 choosable. That is, they're always list colorable with lists of size 2. But this example here shows that even cycles are not flexibly 2 choosable. And I can quickly show that right now. If we wanted to give a proper list coloring to Can you hear me?
I'm sorry, I mishit the button, so I can hear you right now. Please go on.
Can you hear me now?
Yeah, I can
Okay,
hear
okay,
you.
yeah, that's fine.
Yeah.
So if we have a 4 cycle here with these list assignments, and if we have two coloring preferences as indicated by these squares around the vertices, that is, if we prefer to have green here and if we prefer to have gray here, then even if we try to satisfy just one of these coloring preferences, we'll always end up with a green vertex here and a gray vertex here. Then we would have to put blue here and we would have no option left for the fourth vertex. So what this shows is that in this 4 cycle, for any proper list coloring, the proportion of coloring preferences that we satisfy will always be 0. So we cannot satisfy any positive fraction of coloring preferences with the list coloring. So this shows even cycles are not flexibly 2 choosable because there's no positive proportion that can always be satisfied of coloring preferences. Okay, so now that you've seen the meta question, now that you've seen some examples of when it has a yes and no answer, now we can take a look at the direction that people usually take this meta question in when they're doing research. So what I would say the most popular direction is to consider this meta question in terms of planar graphs and also subclasses of planar graphs. But if we consider just the class of planar graphs, we know from a very famous result of Thomason that planar graphs are 5 choosable. But since Thomason's result, there have been many following results that are stronger that show that Thomason's result has a little bit of room for improvement. For example, there are some results saying that if you have a planar graph with lists of size 5 everywhere, and then you have smaller lists every now and then throughout the graph, under certain conditions, those graphs can still have a proper list coloring. Or for example, if you have a graph where you can draw it in the plane and it has crossings, but the crossings are far apart, then those graphs are still 5 choosable. So my point here is that Thomas's result has been shown to have a little bit of room for improvement. So it's natural to ask, can we show that planar graphs are not only just 5 choosable, but can we show that they're flexibly 5 choosable? And in this original paper on flexible list colorings, the authors show that planar graphs are flexibly 6 choosable, but the question of whether or not they're flexibly 5 choosable is still wide open. And it would be very interesting to answer this question, but it seems to be too hard for current methods. All right, so another direction that this meta question can be taken in, which is less popular than planar graphs, but still fairly interesting, is the question of degenerate graphs. So it's known that degenerate graphs are d+1 choosable. And it was shown in the original paper on flexible list colorings that degenerate graphs are flexibly d+2 choosable. But it's still open if whether or not these graphs are flexibly d+1 choosable. And again, this question seems to be very hard, whether or not degenerate graphs are flexibly d+1 choosable, because even for small values of d, like d equals 2, if we were able to prove that, for example, 2 degenerate graphs are flexibly 3 choosable, that would imply some already known results, which are not very easy to show. For example, if we were able to show that 2 degenerate graphs are 3 choosable, then that would show that, for example, outer planar graphs are flexibly 3 choosable. And this is true. This was one of our results, but it was not at all trivial to show this. So again, answering this question seems to be out of current reach of the methods that we have right now. But what we did in our research is we took this question of degeneracy and flexible choosability, and we answered this meta question for degenerate graphs in some special cases. And specifically, we consider the following questions. So the first question we considered is, if G is the class of graphs of maximum degree delta other than the k delta plus 1, we asked, is this graph class flexibly delta choosable? And the reason this is a special case of the degeneracy question is because this graph class G, the way it's defined here, contains all non-regular graphs of maximum degree delta, and those non-regular graphs of maximum degree delta are delta minus 1 degenerate. So an answer of yes to this question would answer a special case of the degeneracy meta question. Similarly, we asked if G is the family of all outer planar graphs. We know that it's 3 choosable because it is 2 degenerate, but we can ask, is it flexibly 3 choosable? And we were able to give a yes answer to both of these questions, and we got the following results. So our first result says, yes, every graph of maximum degree delta other than the clique k delta plus 1 is flexibly delta choosable, and the proportion of flexibility that we got was this 1/2 times delta cubed. And we were able to show that every graph of tree width 2 is 1/3 flexibly 3 choosable. And notice we asked a question about outer planar graphs, and we answered a question about graphs of tree width 2, but since every outer planar graph has tree width at most 2, the answer that we got is actually stronger than the question that we asked. So that's nice. And then one kind of interesting related result that we got, which is also related to degeneracy conditions, is that every graph of tree depth k is 1/k flexibly k choosable. And if you don't know what tree depth is, that's okay, because I'm not going to talk about this result in detail, but essentially, if a graph has low tree depth, then that means you can find it as a subgraph of the closure of a rooted tree, where the closure means you add every possible edge between ancestors and descendants. So essentially it has like a short tree-like structure. But since I'm not going to talk about that, I won't spend too much time discussing that more. What I would like to discuss, though, is mainly this first result that we got, because we thought it was the most interesting, and arguably the proof is the most interesting out of all 3 of these results. And so I'll be focusing on this first result, that every graph of max degree delta other than the clique is flexibly delta choosable. Okay, so let's take a look at how we were able to prove this. So the main concept that we used in our proof is the notion of degree choosability, which some of you may know, some of you may not know. So we can look at its definition. So remember we said that a graph is k choosable if essentially it always has a proper list coloring with lists of size k. Similarly, we say a graph is degree choosable if whenever each vertex v receives a list of degree v colors, then those lists always admit a proper coloring on G. So what that means is we say G is degree choosable if it always has a proper list coloring whenever every vertex of degree 3 receives a list of 3 colors, every vertex of degree 4 receives 4 colors, every vertex of degree 7 receives 7 colors, and so on for each vertex in the graph. So that's what degree choosability is. And the reason that we wanted to look at degree choosability, and the reason that it's so useful to look at degree choosability, is because there's a very nice characterization of which graphs are degree choosable, given by Erdős, Rubin, and Taylor, which is stated right here. And in order to state this result, I need to tell you what a block of a graph is. But essentially, a block of a graph is a maximal connected subgraph that doesn't have a cut vertex. So if you have a graph like this one, then this triangle here is a block because the triangle has no cut vertex. But if you were to try to extend it to a larger connected graph, then you would get a cut vertex either here or there. So for any connected graph, you can essentially think of it as a set of blocks that are glued together or identified at cut vertices. Okay, and then what Erdős, Rubin, and Taylor tell us is that if we have a graph G, then G is not degree choosable if and only if every block of G is either a clique or an odd cycle. And what this means, what this result of Erdős, Rubin, and Taylor means, is that almost every graph is degree choosable, and the only graphs that are not degree choosable are ones that satisfy a very specific structure. And that specific structure of the graphs that are not degree choosable is that they're essentially made of a bunch of odd cycles and complete graphs that are just glued together at cut vertices. So This is going to be useful because if we run into a place in our proof where we want to a graph to be degree choosable, then we'll be able to say, well, if the graph is not degree choosable, then we know it has this very specific structure that Erdős, Rubin, and Taylor describe, where it's just a bunch of cliques and odd cycles glued together at cut vertices. Okay. So our proof isn't very hard, so I will be able to give a complete explanation of what we did. So now I'm going to move into the main idea of our proof for this result. So let's first remember what we're trying to do. We have a graph G, its maximum degree delta. It has a list of delta colors at each vertex, and we would like to show that if we have a set of coloring preferences on the vertices of our graph G, then we can find a list coloring on G that satisfies a positive fraction of our coloring preferences. So the first thing that we're going to do is we're going to ignore most of our coloring preferences. We're just going to forget about them. And we're only going to keep a set of coloring preferences that are at a mutual distance of at least 4. So for example, if this is part of our graph G, and if every one of the vertices in this path had a coloring preference, then what we might do is we might forget all of the coloring preferences, all of these vertices, and only consider a coloring preference at this vertex and that vertex, because the distance between these vertices is at least 4. And since we're working with graphs of bounded degree, we can always take a subset of vertices with coloring preferences that also have mutual distance of at least 4 in such a way that we keep at least a fraction of 1 over delta cubed of our original number of coloring preferences. And since our goal is just to get some positive fraction of coloring preferences satisfied, we don't mind losing a factor of 1 over delta cubed because this is just some positive fraction. Okay, so after we restrict ourselves to coloring preferences at mutual distance at least 4, what we're going to try to do is we're going to try to delete our vertices with preferred colors, which make a set R. We're going to try to delete these vertices with coloring preferences from the graph. We're going to get a graph G minus R, and we're going to try to give G minus R a list coloring. And we're going to do something special with the lists in G minus R. So for example, this vertex has a coloring preference that we haven't ignored, so we say that it is an R. The coloring preference at this vertex is gray. So when we delete this vertex from the graph, we're also going to delete the color gray, which was the preferred color, from the lists of all of its neighbors. Similarly, this vertex has a coloring preference of green, it's in R. So when we delete the vertex from the graph, we're going to delete the color green from the lists of all of its neighbors. And the reason that we want to do this is because if we delete these vertices in R from the graph, then we'll have a remaining graph G minus R. And if we can give a list coloring to G minus R with these modified lists, then we can just stick all the vertices in R back in and color them with their preferred colors. Because if we stick this vertex back in the graph and all of its neighbors are colored with their lists, remember none of the lists have the color gray because we deleted gray from their lists. So we can just color this guy gray, which is his preferred color. Similarly, we deleted green from the lists of all the neighbors of this guy. So when we stick this guy back in the graph, we can color it with green because none of its neighbors have green. All right, so we would like to list color G minus R. So then we can ask, how are we going to list color G minus R? Well, we can notice that if we have a vertex in G minus R like this one that doesn't lose any colors from its list, then it has a list of delta colors. It has a degree of at most delta. So the list size is at least equal to the degree of the vertex in G minus R. If we have a vertex like this one that does lose a color from its list, then it will have a list size of delta minus 1. And it will also have lost a neighbor in R. So it will have degree at most delta minus 1 in the graph G minus R. And therefore, in all cases, these modified lists will have size at least equal to the degrees of the vertex in G minus R. So essentially, if we want to see if G minus R has a proper list coloring, we can just check if G minus R is degree choosable, and then we can use the Erdős, Rubin, Taylor result to try to figure out if G minus R is degree choosable. And actually, it won't hurt us at all to assume that G is delta regular instead of max degree delta. And it won't hurt us at all to assume that this inequality here is actually always equal. So trying to figure out if G minus R is a proper list coloring is the same as asking if G minus R is degree choosable. Okay, so this is the main idea. I realize this proof is a lot, so I'll try not to get into too much detail to bore everybody, but I still want to give a nice explanation of what we did. So what we're interested in is seeing if G minus R is degree choosable and seeing if we can give G minus R a proper list coloring. So we would like to determine some things about the structure of G minus R. So like I said in the last slide, if G minus R is degree choosable, then we are done because that means we can satisfy every preference of the vertices in R, and that's a positive fraction of our preferences. Remember, it's 1 over delta cubed. So if G minus R is degree choosable, then we're happy. If G minus R is not degree choosable though, we know that from Erdős, Rubin, and Taylor that there must be some components of G minus R that have this very specific form. That is, they consist of blocks, which are cliques and odd cycles. And so if we have a bad component of G minus R that's not degree choosable, it must just look like a bunch of cliques and odd cycles that are glued together at cut vertices. So what we can do is we can do some case analysis to try to figure out exactly what these bad components look like. And we'll actually be able to figure out a lot about these bad components. And one thing we can figure out about these bad components is that they cannot just be a single block. That is, they cannot be a single two connected graph. And I won't go into too much detail about why, but essentially, if we have a two connected graph in G minus R that's not degree choosable, that is a two connected component that's not degree choosable, it would have to be a clique or an odd cycle. However, we can show that if it's a clique, it must be a K delta, and it must have a single neighbor in R adjacent to all of its vertices. But in this case, this K delta plus the single neighbor in R would give us a K delta plus 1. And we are not allowed to have a K delta plus 1 in our graph because that would have to be the entire graph. And we ruled out that case in our hypothesis. We're considering all graphs except for the clique K delta plus 1. So we can't just have a single clique as a component of G minus R. Also, if we have just a single odd cycle as a component of G minus R, what we can show is that in this case, we must have delta equals 3. But if we assume that this isn't a clique, then it must be of length at least 5. And then we must have a single neighbor in R. We can show that it has a neighbor in all of these vertices, but then this guy would have a too big of a degree because we have to assume that delta equals 3, but this guy is degree 5. So the long story short is that we can rule out the case that a bad component is a single two connected block. So what we're able to conclude is that every bad component in G minus R must have at least 2 blocks. And through a little bit of more analysis, we can show that every bad component in G minus R must have at least 2 terminal blocks, which are delta minus 1 regular. That is, when I say a terminal block, I mean just a block in the graph, in the component, that has exactly 1 cut vertex. So we must have a block in a component of G minus R that's a K delta with just 1 cut vertex. And the reason for that is if you consider a block in G minus R that has just 1 cut vertex, well, this cut vertex must have some edge going into another block. So that means it has at most K minus 1 neighbors within its own block. However, we know from Erdős, Rubin, and Taylor that every block in a bad component must be a regular graph because it's either a clique or an odd cycle. So that would mean that all of these vertices have to be degree delta minus 1. And from that, we can conclude that this graph, since it has to be a clique or an odd cycle, we conclude that it's a delta minus 1 regular clique, which is a K delta. Okay, but what does that mean? Remember I said we can assume that the graph is delta regular. So if I consider this vertex here, it has only delta minus 1 neighbors within the bad component, so it must have a neighbor in R. Similarly, this vertex, it has only delta minus 1 neighbors in the block. so it must have a neighbor in R. But if this vertex here has a second neighbor in R with a different coloring preference, then something bad would happen. We would get this vertex is in R, this vertex is in R, and the distance between them is 1, 2, 3. And this goes against our assumption that our vertices in R are at distance at least 4. So what we can conclude is instead that this vertex here must have a neighbor in R, and it must be the same neighbor as the first guy. And by following this logic again with this vertex also must be adjacent to the same vertex in R, and same with this one. And we have a vertex in R that has delta minus 1 neighbors in this single block of the bad component. And then since there are 2 terminal blocks, we get 2 vertices in R like this. Okay, but what we can do now is we can apply what's essentially the main idea of our proof. We can ask, there we go. Okay, we can ask what would happen if we went back in time and we took this vertex here and we forgot that it was in R. That is, we retroactively go back in time and we remove this vertex from R. We can ask what would happen then. Well, first of all, since these vertices both had delta minus 1 neighbors in these k deltas, these 2 vertices that were in R, they cannot have delta minus 1 neighbors in the terminal blocks of any other bad component. So essentially, we can say that these 2 vertices in R, they corresponded uniquely to this one bad component. So we can say that the number of vertices in R is at least twice the number of bad components. Second, we can say if we removed this vertex here from R, then if we look at what the new graph G minus R would be, it would have, it would contain all of these vertices right here. And what we can observe is that these vertices would belong to a block that is neither a clique nor an odd cycle. And what that would mean is that this whole bad component here would no longer be a bad component because it would not have all blocks that are cliques and odd cycles. And therefore, this whole component in the new G minus R would be degree choosable. And essentially, the idea is we only had to destroy 1 out of these 2 neighbors in R in order to rectify the bad component into a good component. And what that means is if we do the same thing to all of the bad components, we can destroy at most half of the coloring preferences in R in order to rectify all of our bad components into good components. And then G minus R is degree choosable. We give G minus R a proper list coloring, and then we can satisfy the preferences of at least half of the vertices in R, because we destroyed at most half of the vertices in R with our coloring preferences, so we can satisfy at least half of the preferences. And we end with this fraction of at least 1/2 delta cubed of our coloring preferences satisfied. I know that was a little bit involved for a talk, but this is the main idea that we had. If you zoned out during that explanation, you can zone back in and you won't be lost anymore. And yeah, so that's the end of our proof, and that was our main idea. So what I'd like to say about this, we were very happy with this result and this method, by the way. We thought it was really cool. And one thing that we noticed about this method is this is an algorithmic method. That is, if you gave me a graph that has maximum degree delta, that's not the clique k delta plus 1. And if you gave me lists of size delta on each vertex, and then if you gave me a set of coloring preferences, then I could follow this method step by step, and I could give you back a list coloring on the graph that satisfies at least that positive proportion of your coloring preferences. That is, I could satisfy at least a fraction of 1/2 delta cubed of your coloring preferences. And that's because the proof that we had tells you exactly how to get the list coloring that satisfies the coloring preferences. And what we noticed is that our method that we had is quite different from a lot of other methods that people often use to attack the flexible list coloring problem, because the most common method that other people have used to approach this list coloring problem is a probabilistic method. And what they do in the probabilistic method is if you have a graph where every vertex has a list of possible colors, then what you try to do is you try to show that you can give your graph a list coloring randomly, and you try to show that for every vertex in the graph, and then every color on the list of that vertex, you can put this color C at the vertex V with probability at least epsilon. And if your lists are size K, then this would show that your graph is epsilon flexibly K choosable. And that result will just follow from a linearity of expectation argument. But essentially, what people often try to do is they try to just show that this probability holds for every vertex and every color on the vertex's list. But this method doesn't actually tell you how to get a proper list coloring that satisfies a positive proportion of your coloring preferences. So we thought it was interesting that we came up with a method that is algorithmic and does tell you how to get an appropriate list coloring. And we think it might be interesting to see if an algorithmic approach can work on other problems in flexible list coloring. So what I'm going to do now is just going along with this idea of algorithmic approaches. I'd like to just show one other algorithmic approach that we came up with for another class of graphs. So remember, we also considered graphs of tree width 2. And in order to explain our method for graphs of tree width 2, I'll just define what a 2 tree is. So a 2 tree is a graph that you get by starting with a K2, like this, and then just by adding vertices of degree 2 whose neighbors form an edge that's already in the graph. So I add a new vertex, and I give it 2 neighbors that form an edge that already exists in the graph. And you can keep adding vertices of degree 2 as long as you want. You can add a vertex degree 2 to the same edge multiple times. And that's how you get a 2 tree. And then the subgraphs of 2 trees are what we call graphs of tree width 2. And there are other characterizations of graphs of tree width 2, but this is the one that we worked with. Okay, but what we were able to show for graphs of tree width 2, that is for 2 trees, is that if you consider a graph of tree width 2 that contains a triangle, and if you assume that all of the lists at each vertex have the same set of colors, that is, if you just go back to the normal graph coloring problem, what you notice is that, I'll just give a quick example with this triangle. This triangle, for example, it has 6 possible colorings. Like you could, it would take too long to draw all of them, but like you could put red at the first, you could put red at the first vertex, then gray at the second vertex, then black, or you could have red, black, gray, then you could have gray, red, black, red, and then you would have 2 others starting with black. And what you would notice is that a certain property would hold for this set of 6 colorings at each edge. And what would hold is that, first of all, you would get 6 possible colorings. Second, you would notice that each color on each list appears exactly twice at each vertex. So that is, there are 2 colorings that use red here. You can have red, black, or red, oh, there's no gray, that's fine. Whatever, you could have red, black, or red, gray along this edge. And that would make red appear twice at this vertex. And then for any color down here, you would have the same property. You would have exactly 2 colorings that make any given color C appear at this vertex. And you would also notice that no ordered pair would appear twice. So like you wouldn't get 2 colorings that have red, black, because that would force gray twice at the third vertex, and then it would just be the same coloring. So you would never have the same ordered pair appearing in 2 distinct colorings. So what we thought is, what if we can try to make these properties hold at every at every edge of a 2-tree graph, even if all of the lists are not the same. And what we were able to show is that we actually can do this. So what we were able to show is that if you have a set of 6 colorings that satisfy these 3 properties at some edge of a graph, And then if you add a new vertex to the graph like this one, and you make it adjacent to an edge in the previous graph, then you can always extend the 6 colorings to satisfy these 3 properties at each of these 2 new edges. So I gave an example here. I have a vertex here with a color list brown, blue, red, and another vertex with color list green, purple, brown. And we have these 6 colorings that satisfy the 2 properties, and the 3 properties. We were able to show that as long as these 3 properties are satisfied at the first edge, they can always be satisfied at the new 2 edges with some extended coloring. And I actually wrote down how to do this, but I appear to have lost the piece of paper between the time that I wrote it down and the time that I set up this talk. But the way you would do it here is you would put, let me see if I can do it really quickly. You would put red here, then you would put red here, and then you would put, I believe you'd put purple here, and then you would have a green here, and then green here, and then the point is you should be able to extend these 6 colorings into you should be able to extend the 6 colorings at the edge into a way that colors the 3rd vertex in each coloring, and you should be able to satisfy these 3 properties at each of the new edges. So if you look at, for example, all of these pairs at this new edge, all of the properties should be satisfied. And if you look at all of these pairs, all of the properties should be satisfied. And what we showed is that no matter what the coloring looks like at the first edge, as long as it satisfies the properties, you can extend it to satisfy the properties at the new edges. So I'm not sure if I did it right in the colorings that I drew, but the idea is we can always extend. And since any 6 colorings where every color appears exactly twice at a vertex must satisfy every coloring preference exactly twice, that would mean that one of these 6 colorings must satisfy at least a third of the coloring preferences. Okay, so the point that I'm trying to make with these algorithms is that in each case, we had a certain graph structure, and we were able to exploit some property of the graph structure in order to find an algorithm that actually returns a proper list coloring that satisfies a certain proportion of coloring preferences. So we think it would be interesting if there are other graph structures for which there exist algorithms like this, where you can input a graph, you can input color lists, and you can input a set of coloring preferences. And if the algorithm can actually return a list coloring that gives you, that satisfies a positive proportion of your coloring preferences. Okay, so I guess I'll end the talk with just these 2 open questions that we think would be very interesting to answer. So the first question that we thought of is, we could ask which graphs are flexibly degree choosable. So we defined a graph being epsilon flexibly k choosable. We could similarly define a graph being epsilon flexibly degree choosable. And we could ask which graph classes are epsilon flexibly degree choosable for some universal constant epsilon. And we saw Erlich, Rubin, Taylor give a very nice characterization of which graphs are degree choosable. So it's possible that there's a very nice characterization for the graphs that are flexibly degree choosable. If such a characterization exists, though, we don't think it would look very much like the Erlich, Rubin, Taylor characterization. And the reason for that is certain graphs that are degree choosable by Erlich, Rubin, Taylor are not flexibly degree choosable. For example, the even cycles are not flexibly degree choosable. Also, the diamond graph, that is the K4 minus 1 edge, that is degree choosable by Erlich, Rubin, Taylor, but it is not flexibly degree choosable. So any answer to this question that gives a nice characterization would probably look a lot different from Erlich, Rubin, Taylor. All right, the other question that we asked is, are K trees flexibly K plus 1 choosable? We showed that this is true for K equals 2, but even for K equals 3, it seems like it might be possible with a lot of case analysis, but it doesn't seem very easy. And for higher values of K, it seems like it would be quite hard. And we even tried this question just for the restricted graph class of k paths, which is what you get when you take a path and you add an edge between vertices that are at distance at most k. But even just for k paths, the question of whether or not they're flexibly k+1 choosable seems to be fairly difficult. All right, so that's the end of my talk. Thank you everybody for your attention.
Thank you, Peter. Very nice talk. And if you can unmute yourself, let's clap for Peter. Any question?
I have two questions actually. So first of all, congratulations, Peter.
Yeah.
I just wondered, because I don't know that much about graph theory, but I noticed something might be interesting. On your three theorems, the slides of your three theorems, I noticed something.
Yeah.
Yeah, like the second theorem, you choose to the tree width to be 2, and then the tree depth to be k. Why is it so restricted to be 2? Like, have you generalized that?
Okay, so the reason we needed tree width to be 2 is because in the case of tree width 2, we had essentially we got very lucky in finding out that if we have 6 colorings that satisfy these properties at an edge, we were lucky to realize that it can always be, that the 6 colorings can always be extended to a third vertex such that the properties are still satisfied at the new 2 edges. And we tried to come up with similar properties that would work for graphs of tree width 3. And the way you would have to approach the problem for graphs of tree width 3 is you would say, if you have some property that's satisfied by some set of colorings on a triangle, you would say, well, if you add a new vertex that has neighbors forming a triangle, you would say, can you show that the properties also hold in all of the new triangles? And we tried to come up with a set of properties that would extend to these new triangles, but we were not successful.
Yeah, because it's planar graph. What about 3D for that?
I'm sorry?
What about 3 dimensions in the? Because it's
Oh,
graph, right?
I think, I guess here the way that I draw it doesn't matter. When I say like every new triangle, I mean just like every 3 cycle that's added when I add this new vertex. And like this triangle. Sorry, it's hard to draw on here.
Yeah, because what I see there is a 3D tetrahedra, and it might work in higher dimensional. So that's, yeah, anyway.
Right. I think I know what you mean. Like if this were instead a K4, like that, and then if you added something with 4 neighbors, then it would look like a higher dimensional polyhedron. Right, but the main challenge is finding properties that can be inductively extended to new parts of the graph. And we just got very lucky to notice that these properties could be extended. The initial way that we figured out that these properties could always be extended to new edges was just by testing every possibility with a program and brute forcing it. But we've had trouble coming up with similar properties that would work for higher tree width.
So the second question is, what's the complexity of your algorithm?
So the polynomial time, maybe Tomasz could answer this better than I could. The tree width algorithm is linear. The maximum degree, okay, you can get this at R in linear time, then you can, for the underlying list coloring, that might be quadratic. Yeah, okay, I think it's at worst quadratic.
In what variable?
Oh, in the number of vertices of the graph.
Great, thank you.
Yeah, thanks for your question.
Any more question or comment?
Yeah, I have a question. So Peter, for the, was it half over delta cubed is, do you know if that constant can be brought higher, like that particular value of epsilon?
Yeah, that's a great question. Blaine actually recommended that we try to improve this constant. So we came up with a more complicated proof where this constant can be improved to 1 over 6 delta. So we're not sure if the 6 is best possible, but being of the order 1 over delta is best possible because you could consider a graph that's like k delta, and then joined by a perfect matching. And then if, for example, you prefer the same color on every vertex of this 1k delta, then the best fraction that you could hope for would be 1 over delta. So yeah, it's a great question. And that's where we are right now with the constant.
Awesome.
All right. If we do not have any more questions, we can go to the sharing session. And I believe Peter would like to talk about how he made his mind to study mathematics. Peter, please.
All right.